Example 1.2. On average, each person in the industrialized world is responsible for the emission of 10,000 kilograms of carbon dioxide every year. This includes CO2 that you generate directly by burning fossil fuels to operate your car or your furnace, as well as CO2 generated on your behalf by electric generating stations and manufacturing plants. CO2 is a greenhouse gas that contributes to global warming. If you were to store your yearly CO2 emissions into a cube at standard temperature and pressure, how long would each edge of the cube be? Well, we know that CO2 is a gas, so that means we're going to treat CO2 as an ideal gas. So treating CO2 as an ideal gas, we can calculate the volume of a cube of CO2 using the ideal gas law. So what I'm really looking at here is that I imagine that I have a cube. So let's say that this is my cube right here. And so when I'm looking at my cube, what we want to do here is that this volume tells me that I have some particular length. And the ideal gas law says that this has to be nRT with ideal units. And you can see here is that this guy right here is what we call the volume. And the volume would then be L cubed. So that way, this allows me to compute that. And you could see by looking at this thing, we know everything but the number of moles. So standard temperature and pressure immediately implies that we're at 20 degrees C at 1 atmosphere. But that's not proper units. So I need to convert to proper units. So if I convert to proper units, I could see here that the Kelvin temperature, which is the Celsius temperature, but plus 273, I'm going to get 20 plus 273, which gives me 293 Kelvin. And then the pressure, which is at 1 atmosphere, converted into pascals, is 1.01 times 10 to the 5 pascals. So I know the temperature, I know the ideal gas, I know the pressure. You can see here is that we need to determine the number of moles. Okay, the number of moles in some volume. So since we're using proper units, I'm going to assume, okay, I'm going to assume the cube is 1 meter cube. That does not take away from the problem. So here we go. So I'm going to calculate the number of moles first. because that's what I need. So here we go. So the first thing I got to do is that I have to calculate the number of moles in 1 meter cube. So again, I got to use the periodic table. No, I just got to calculate the number of moles. Okay, so if I look at the number of moles here, it's got to look something like this here. So I'm going to use the periodic table again. To get the molar mass of CO2. So if you look at CO2, it really looks something like this here. You're going to say that I'm going to have some, it's a linear molecule. So I have oxygens right here on the side. And then here in the middle, I have a carbon. So it has 3 molecules. So what I'm going to do here is that from the periodic table, here's what I have. You could see here that here's my atomic mass of carbon. Here's my atomic mass of oxygen. So then I could see then that the mass of carbon then reads what? 12 grams per mole, but not in the right units. So I got to put this into kilograms. And as we saw before for oxygen, this was 16 times 10 to the minus 3 kilograms per mole. So with these masses, I could now calculate the molar mass. So the molar mass of CO2 is then going to be this. So then I have the molar mass. So this is going to be the mass of carbon plus 2 times the mass of oxygen. So then this will be what? This is going to be 12 plus 2 times 16 times 10 to the minus 3 kilograms per mole. And so this gives me 32 plus 12 gives me 44 times 10 to the minus 3 kilograms per mole. So that is the molar mass of carbon. So now that I have the molar mass of carbon, then I could then come in here and do this here. So then the number of moles of CO2 is then going to be this here. So then the number of moles of CO2 should be the mass of the sample divided by the molar mass. Now here, this is then going to be the mass of CO2 divided by the molar mass of CO2. And so when I compute that, so what's emitted, they tell us that the amount of CO2 emitted is 10,000 kilograms. So then this is going to read, so if I look at these numbers here, I'm going to have what? 44 times 10 to the minus 3. And that's going into 10 to the 4. Now note that this is in kilograms per mole. Immediately we see that there's a cancellation of the kilograms. So the number that we get here is then going to be 2.27 times 10 to the 5 moles. And that's the number of moles of CO2. So now that I have the number of moles, I could then go in and use the ideal gas to calculate the volume. Okay, so remember, the way I'm going to use this is that I'm using the standard temperatures and pressures to actually do that. So then here I go. So now we're going to use the ideal gas law to calculate the volume. So now that we're here, that means then the volume of the CO2 cube is PV equals to nRT, and that allows me to solve for the volume, which is then going to be nRT divided by P. So then we start putting in our numbers. So then this tells us here that this is going to be 2.27 times 10 to the 5 moles. Then I got to multiply that by the gas constant, which will be 8.31 joules per mole times Kelvin. And then the temperature was 293 Kelvin, all divided into atmospheric pressure, which is 1.01 times 10 to the 5 pascals. So when you're looking at this unit-wise, here's what you're seeing. Note that the mole here is in the numerator and that guy's in the denominator. And then you look at the Kelvin's in the numerator here, and this is in the denominator. So that means then joules per pascals is going to be in units of meters cubed. So if I compute this number, I end up getting to 2 sig figs, I get meters cubed or 5,100 meters cubed. And this is the volume of the CO2. So then the length of the cube is then going to be that the volume of CO2 is going to be L cubed. So then solving for L, this means I need the volume to the 1/3 of CO2, which then gives me 509 meters cubed, and this is 1/3. And then I get 17.2 meters. So this is the length of the cube.